Hello and welcome to this film about kinetics. It's the first of three films about reaction rates, which is what kinetics is all about. It's the study of reaction rates. Hopefully before you watch this film you've already seen the film about energy changes in chemical reactions, because this one will talk about energy changes and it's good if you already know about those. And hopefully by the end of this film you'll know some of the key terms that we use when we're talking about rates of reaction, and also you'll be able to see where these key terms fit into those energy level diagrams which you might have seen in the energy changes film. Okay, so the energy level diagrams that we're going to look at, they're going to be quite similar to the ones we've seen before, but there's going to be a couple of extra features, and they are activation energy, so how much energy you need to kind of activate a reaction, or in other words how much energy we need to put in to get a reaction started, okay, and something called a transition state, which some people call an activated complex, okay, but they're the same thing. Okay, so here we go, let's have a look at a couple of energy level diagrams and let's start talking about these terms which we've just introduced. Okay, this should look familiar to you, this energy level diagram, because it's one for an exothermic change, so one where the reactants are higher than the products, okay, and remember the difference between these two levels. So although there's some other stuff on this graph, right, remember that your energy level diagram showed you that the difference between those two levels was called delta H, or the enthalpy change, so enthalpy being this kind of chemical potential energy that we've looked at before, and the reaction pathway being the progress, so start and finish. So we're going from reactants to products, the enthalpy is falling, so delta H is negative. Remember, delta H is negative for exothermic changes, okay? But here we can also show something called the activated complex, so that is this kind of brief well, it's a complex molecule basically, but it's basically it's a kind of halfway house between reactants and products. Okay, and it's a high energy state, which some people call a transition state. Okay, doesn't matter which of those terms we use. But the energy that we have to put in to get from reactants up to this activated complex is called the activation energy, and we give that the symbol EA. Okay, so there's our activation energy. It's the difference in height between the reactants where we start and the top of the hump that we have to get over in order to get to the product. So in other words, it's the minimum amount of energy we have to put in to get a reaction started. Okay, so in green there you've kind of got the levels that you would have seen on an energy level diagram up until now, and we've got the enthalpy change there. All we've done is we've just added what happens to the energy as we proceed through the reaction. So as we go through this transition state, or this high energy complex called an activated complex, and we've shown that the difference in the difference in height between the reactants and the top of the hump, or how much energy we have to put in, that is called the activation energy. So let's have a look at those things on an endothermic reaction profile, or an endothermic energy level diagram. Remember, on an endothermic change, the reactants will be lower than the products, so the potential energy, or the enthalpy, will have risen. So the difference in height between those two levels there, which is marked C on this graph, okay, that is the enthalpy change. And you might remember, hopefully, that the enthalpy change for endothermic processes is positive, okay, because it's gone up. And here, once again, we can see that there is an activated complex, okay, or the transition state, and the difference in height between the reactants and the top of this hump, or in other words, the amount of energy we have to put in to get the reaction started, and this diagram it's labeled A, that's the activation energy, EA, okay? So once again, we can see the activation energy as the difference in height between the start and the top of the hump. It's how much energy we have to put in to get to the products, okay? So although there's this enthalpy change, we might have to put in more energy than that to actually get the reaction going. Okay, what we're going to do now is we're going to look at how these things, the activation energy and the transition state, more specifically the activation energy, relate to how fast the reaction will happen. Now hopefully you can kind of imagine that if a reaction doesn't need a lot of energy put in to get it started, it's more likely that it will get started at sort of lowish temperatures like 25 degrees centigrade, a normal room temperature. So if we've got two reactants together, here we've got H2 and Cl2, okay, we're looking at an exothermic change here, right? So there's the enthalpy change, okay. What we can see here is that the activation energy for this process is small. Okay, so you don't need a lot of energy to get this reaction started, and so it's likely to be spontaneous. Okay, it's likely to just happen without you having to provide a spark or without heating it up. Okay, here we've got what is quite an unusual thing. It's an endothermic change. Okay, we've got delta H marked here. It's positive because it's increased, right? Going from reactants and products to products. And we could also mark the activation energy on here. Now it looks like the activation energy is quite large in this case, okay, simply because of the scale that the diagram is drawn on. Okay, this is an unusual change. It happens in an ice pack. If you dissolve ammonium nitrate in water, you'll form ammonium nitrate aqueous. Okay, so this dissolving process is actually endothermic. It's quite unusual because it's an endothermic process that happens spontaneously. Okay, which means the activation energy must be quite small. Okay, even though it might not look like it on this diagram because of the scale of the diagram, because in fact the enthalpy change is quite small for this process too. Okay, moving on, we're having a look at some slow or non-spontaneous reactions. Well, what must be the case here? Well, I guess the activation energy must be quite large. Okay, now this doesn't look large compared to the last energy level diagram that we've looked at, but the enthalpy change here is quite large. So by considering the scale of this diagram, we can see that actually this, although it might look small, could be quite a large figure. Okay, this is actually the energy level diagram for methane burning in oxygen, okay, and producing carbon dioxide and water. Okay, it's an exothermic change. It releases a lot of heat. Okay, but luckily for us, in a sense, because we can turn the gas tap on without it just going bang straight away, this reaction won't start until you provide some heat energy, usually in the form of a spark or a match to get the gas burning. Okay, so this activation energy must be quite large, and for large activation energies, reactions won't be that fast, or they won't take place of their own accord. They won't be spontaneous because we need so much energy to get them started. Okay, here's another endothermic change, and again we're showing the activation energy here. It's the difference between the start and the top of the hump, and it doesn't matter whether we're talking about an endothermic one or an exothermic one. What we're looking at to decide whether a reaction is slow or non-spontaneous is the size of this activation energy here. Okay, so if it's a large activation energy, it's unlikely that particles will have enough energy to react at low temperatures. We'll have to give the reaction a bit of a kickstart. Okay, now the next two films that we watch about kinetics, they're going to be to do with the collision theory and what particles actually have to do to react. So I've just touched on that here, that particles have to collide with a certain amount of energy. Okay, so they're the next two films to watch, and that's it for this one.